So here are the graphs for number 12 and 13 on the practice problems for section 3. So here's part A is to use crucibles and part B is to use prims starting at A. And again, part A is to use crucibles, part B use prims starting at Y. So let's finish up our last section here. All right. So matrix representation of graphs. So if I have this graph here, this graph right here, I'm going to be making a 3 by 3 matrix because I see I have 3 vertices, right? V1, V2, oops, I guess I forgot to label this guy, V3. Okay, so there's 3 vertices, so it has to be a 3 by 3 matrix because each of the places is going to tell me how many edges there are from one vertex to another. So this is, you remember from matrix land, A sub 1, 1. So this would be, this is the number 1 here because there is one arrow from V1 to V1, right? One edge, one number of arrows into, right? The number of arrows, not the edges, number of arrows. Okay. So let's look at this one. So A1, 2, this is the number 0 because there are no arrows from V1 to V2. So notice there's V2 to V1, but there's no arrows from V1 to V2. That's why this is a 0. This is a 0 also. So this would be A1, 3. There's no arrows from vertex 1 to vertex 3. Okay, so let's look at 2, 1. So 2, 1 would be this. So row 2, right, column 1, then that's the number 1 because there's one arrow from V2 to V1. So from V2 to V1, there's one arrow going in. Let's look at this one that says the number 2. It's a little bit different. So there's 2 arrows going from V2 to V3. So from V2 to V3, I have 2 arrows, right? So that's where the entries come from. All right, so I'm going to let you do these 2 for Zoom. I want you to draw the graph. And looking at this, so this is a 3 by 3 matrix because there's 3 vertices, 4 by 4 matrix. Wait for it. 4 vertices, right? And this is Zoom, so both of these are zoom. This one is not directed, right? It's undirected. There's no arrows on the edges, so it's going to make the count a little bit different. So it's going to be the number of edges. If it's undirected, then you're just counting the edges. Directed, you're counting the number of arrows. All right. So here, if I've got a matrix, and I've got the matrix to a power, so if I've got the adjacency matrix for a graph is A, if I take the matrix to a power, like cubed, so so I'm taking A, putting a cubed in the calculator, the entries in this matrix now tell me the number of walks of length n, so this would be the number of walks of length 3 from one vertex to another. So how many walks of length 3, A cubed, so we're looking at the right matrix, are there from V2 to V2? So that would be the number 4, right? So here I give you A to the 4th power, here I give you A squared, so I'll let you do both of those on Zoom. All right, so now we're going to go into isomorphisms. So isomorphisms are showing that there's a similarity, there's a relationship between, so it's going to be 1-to-1 and onto because it's a 1-to-1 correspondence, a 1-to-1 onto from the edges, the vertices in G to the vertices in G prime. And then from the edges in G, right, to the edges in G prime. So I need to match them up so that they have the same degree and that there's a relationship. So let's start with vertex V1. So vertex V1 here has a degree of 4. So I'm looking over here to see which vertex has degree 4. There's only one. So that's got to go to here. Right? All right, so let's look at V2. Just moving along my graph here. Where is V2? Here it is. There's V2 right here. V2 is here. It has degree 2. So I'm looking for a vertex that's connected with V1 It goes to V2, so looking for a vertex that's connected with W2 and has degree 2. So I think I want to go to, I could go to W3 or I could go to W1, right? Either one of those. So I'm just going to have it go to W3. So it's not necessarily unique, as you can start to see. All right. So let's see what V3. V3 is here, so this has degree 3. So I need to find a vertex of degree 3 that is connected to W2, right? So that's going to be, oops, I drew my graph wrong. Oh, shucks, there it is. I'm supposed to have this little thing here and then this little thing here. All right, now that helps. All right, so V3 is here, and it's supposed to be has to have a degree 3 and has to be connected to V1, so that looks like I'm going to go to W1. So V3 goes to W1. All right, then V4 has degree 3, so I'm thinking that's going to go to W5. And then the vertex 5 here has degree 2, and W4 is degree 2. So there it is. So I've got the vertices all matched up, and I'm going to let you do the edges for fun. All right, so then coming down here, we talk about something being an invariant. If it's an invariant, that means there's something on G that's not on G prime. So these are all the big deals. So an isomorphism is showing really there's a similarity between the graphs as I connect that vertices and edges, correct? So these, if there's an invariant, so if one graph has 10 vertices and the other graph has 5 vertices, that's an invariant. There's no way I'd be able to find an isomorphism. They have to have the same number of edges, and they have to have a vertex of degree k. So if one vertex has a vertex with degree 3, this one has to have a vertex with degree 3. M vertices of degree k, a circuit of length k, simple circuit, connected, Euler circuit, Hamilton circuit. So if you can find something that's different between the two graphs to say, oh, here's the invariant, then you can say that there is not an isomorphism. So I'm going to let you do these on Zoom. So find the invariant between G and G prime, and find the invariant between H and H prime. And I've given you more to play with on this page as well. So then you can copy those down. So there's your G, and there's your G prime, and here's your G, and here's your G prime. So find the invariant between these two, or show the isomorphism. And then here, the edges are not labeled, but you get to do the same thing.